All right, so let's check out the practice problems. And so looking at the first one, we got a football player kicks a football in a field goal attempt. When the football reaches its maximum height, what is the relationship between the direction of the velocity and acceleration vectors? And as always, we'll just assume there's no resistance. So, shoot your football at the top of the height. So that's what we're interested in, the top of the height. So at the very top here, the velocity going this way, it's going perfectly horizontal, while the acceleration vector due to gravity is coming straight down at the very top of the height. Remember, max height. Remember max height. So our max y is when our velocity is 0 in the y direction. So at the top of the height, there's no velocity going up or down. At the top of the height, the velocity is entirely to the right, and any acceleration due to gravity is straight down, so we have a 90-degree angle that's there. And that's probably what they're looking for. Max height, velocity, and acceleration point in opposite directions? No. If velocity and acceleration point in opposite directions, then your object slows down because acceleration is against your velocity, so that'll cause your motion to slow. At maximum height, both the velocity and acceleration are 0. Well, if there's zero, it's funny to me, because if the acceleration and velocity was 0 at max height, then the object would just stay there floating, because if there's no velocity, it's not moving, and if there's no acceleration, then there's nothing to push it to move. It would literally just float there, so that's certainly not what happens. At the maximum height, velocity and acceleration are perpendicular. That's what this picture is. The velocity and acceleration are perpendicular, so C is our correct answer. And let's just check out what the last one is. The velocity and accelerations are parallel. So this is a case for parallel. Parallel could mean it's slowing down. A parallel could also mean this, where the acceleration and velocity are in the same direction. That means things would be increasing, its speed is increasing. Like when your car's at a stoplight, you give it acceleration, and then your car moves in the direction of that acceleration. But remember, the acceleration here is from gravity. It's entirely down, so it's never in the direction of this horizontal component. So that's our answer, the third one there. Check out the next one. All right, checking out number 2, a projectile launched horizontally. So there's our projectile launched horizontally. Horizontally means it has no vertical component. So the velocity in a y direction, up or down, must be 0, at least initially, because they don't tell us if it's being shot along the floor or off the table or something. But for it to move horizontally means there's no velocity going up or down, otherwise it would move up or down. So let's see what choices we got here. A projectile launched horizontally. The vertical component of the projectile's velocity continually in... Oh, boy. Man, some of these answers really depend upon if I'm shooting it off a table or if I'm just on the ground shooting it. Let's see. Let's go through, see what's going to happen. So this first one says a vertical component of the projectile continually increases. Okay? Well, if I shot my object off a table, well, the initial velocity in the y direction is 0. So that's certainly true. But as the object falls, the y velocity will get larger. Now it'll increase into the negative direction, but they do say magnitude. So this first one is true if we're shooting it off a desk or a table or something. But that's not going to be true if I just shoot my projectile along the ground. The vertical component of the now projectile does imply to me it's going through the air. Just to be clear, because you're using the word projectile, so it does apply to me it is going to fall through the air at some point. The vertical component is initially decreases and then increases. Well, I can't. Can I even imagine a scenario like that where it increases and decreases? I really can't. I'm not going to think too long about it because the longer you have to try to imagine a scenario, the more likely it's probably not true. So there's all the thing I'm going to do on that. Can it decrease and then increase? I mean, not being shot horizontally. I can imagine a scenario like that if it's shot at some angle, because then the velocity would decrease as it gets higher, but then as it falls, it would increase. So that would satisfy the second statement. If I shot it at an angle, then the velocity will slow down till it gets to the top, and then the velocity will increase in the y direction as it falls. But it does say it's being shot horizontally, so that's this picture. This is not horizontal shooting, so I'm going to ignore the second one there as being wrong. The vertical component remains a non-zero constant. The velocity remains constant. The velocity is not constant through projectile motion because there's an acceleration. So how do we know the third one is wrong? Because we know there's an acceleration due to gravity, and that acceleration is going to change the velocity, which means it will not remain constant. The vertical component is always zero. Well, this is true if I'm shooting it along the floor. So if I kick a little toy along the floor, well, its velocity in the y direction will be zero and remain zero. I don't think people would consider that to be projectile motion, no. Projectile motion means it's falling through the air. So I'm going to ignore 4 as being wrong as well because we're not kicking things along the floor. And finally, the vertical component continually decreases in magnitude. Continually decreases in magnitude. Wow. Well, that's approaching some calculus idea that something can forever decrease in magnitude means it gets forever and ever closer to zero. I don't even know what they mean by that. The first one's really the only good answer here. And this is, I don't want to say this is necessarily some fact of physics. I don't want to claim that. But it tends to be true the more you have to kind of imagine some fantasy world where to try to make something happen probably means you're getting farther and farther away from the real physics answer is. So that's what I say about this last one. Maybe I could think of some way that an object continually decreases, but it wouldn't be for something that just like simple projectile motion. So we got for the next one. A pilot releases a package from a plane flying horizontally. So, all right, here's our plane. No reason to be a good artist or anything. We just need to get the picture across. There's my plane above the ground. It's flying horizontally at some constant speed. And it releases a package. So it's going to release a package. Now, imagine two scenarios here. First, imagine you're in the plane. So if you're in the plane and you drop this package, well, the package is going to keep with your same velocity, but it's going to fall like this. From your perspective, in the plane, the package is always underneath you. So as the plane moves to this point and you're standing on the plane, you'll still see the package right underneath you. So from your perspective in the plane, the package is always beneath you because you and the package have the same velocity. The plane's flying this way and your package is going this way with the same velocity. So from your perspective in the plane, it looks like the package just falls straight down. But from an observer on the ground, they're going to see the package going forward with the plane's velocity, but of course they're going to see it fall. And a person on the ground will see this arc then from the ground. But from the plane's perspective, you would see the package just fall straight down. When a package reaches the ground below, what is the horizontal location of the plane with respect to the package? Well, it'll be right above it. So let me just say this again. The plane has some constant velocity. The package also has that same constant velocity because it's in the plane. So when you drop that package from your plane, well, you both have the same constant velocity forward. And again, remember, we're ignoring air resistance. So these both have the same velocity. And when the package reaches the ground, well, the plane's going to be right above it because they both have the same velocity. So, whatever, the package will be ahead. The plane will be located behind. No, the location of the package was dependent. So that right here, the plane will be located directly above the package. And let me just say this about a problem like this, because this is, I think, a pretty good problem. But what makes this a little bit more challenging is you know that there's actually air resistance. So how air resistance affects this will really depend on what these objects looks like, since air resistance is dependent upon an object's shape. But without air resistance, these two have the same velocities and they'll always be in the same position. Imagine you're driving on the freeway and two cars are doing the same speed. Well, when they get to the stop sign, they'll both get there at the same time because they're both doing the same speed. Same scenario here. The package and the plane have the same forward speed. So when the package hits the ground, the plane will be right above it. So pretty good question, but it does take a little bit of imagination, I guess, to ignore the air resistance part. Because, again, you do know that air resistance is real, and that can be a challenge sometimes in trying to ignore what you know is real. So let's check out this next one. A tennis ball rolls off the edge of a table. All right? So here's our tennis ball rolling off the edge of a table. So rolling off tells us something right off the bat. It tells us the initial velocity in the y direction is 0 because it's just rolling off. We're not throwing the ball down. We're not throwing it up. The ball is just going to roll off the table, which means its initial velocity in the y direction is 0. We also know the acceleration is due to gravity, minus 9.8, so we can write that in. If we look at the little blue part, we see the table is 0.65 meters high, which means the ball will fall minus 0.65 meters. That's how far the tennis ball will fall. It'll fall into the negative direction, which means it's going to displace a negative 0.65. And then it says it strikes the floor at a point 1.1 meters from the edge. So that's our x direction. So they're telling us x is 1.1. And remember, the x direction only has one equation for projectile motion, and that's x equals vt, because there's no acceleration in the x direction, which means this is our only equation for the x direction. And we already know that x is 1.1, and so we can get that equals vt. There's supposed to be a decimal in there, 1.1. And to solve for velocity, we'd have to know time, which actually is the question to part A. Part A says, find the time of flight. Okay? Well, we have these three. An equation that's used a lot, if you haven't noticed yet, is this particular one. These equations, I don't know, they don't have really any physical names. It's just a quadratic equation. And we know that the displacement minus 0.65 We know the acceleration due to gravity, minus 9.8. We're solving for time in the air. And the initial velocity is 0 because it was just dropped. And so here's what we're solving for, minus 0.65. Now half of 9.8 is 4.9. Divide both sides by it. And that's our value then for t. So let me check that out really quick. We got 0.65 divided by 4.9. So, oh, actually, I need to take the square root of that, though, because t is squared. And we get 0.36. So our time here is 0.36. And I'm just going to take it to 2 decimal places and just type that number in. And then it says that it's either rounded differently or I didn't use correct significant figures. So 0.364. And again, I'm not penalizing you for sig figs. So that's what they're telling us here. I didn't use proper significant figures. This should be technically be 3. And I can see that from the data. But again, I don't want to penalize you for sig figs. So just take 2 or 3 decimal places and, that should be good. Let's check out part B. Find the magnitude of the initial velocity of the ball. All right. Well, going back to this equation here, so remember, the ball had no velocity in the y direction. All its velocity is in the x direction, and we can now get that from this equation. Since we know the ball traveled 1.1 meters in a time of 0.36, and I'll use their number 4 there, we can solve for v. It's just 1.1 divided by 0.364. That is then our velocity. And so what is that? It is 3.02. And so there we go. What's the magnitude? 3.02. They just had to have the 02 in there, huh? It couldn't be a perfect 3. No, it couldn't be a perfect nice 3. It's 3.02. Of course, numbers can be anything, but Let's see what the next part is. It says, find the magnitude of the velocity of the ball just before it strikes the floor. So this one will take a little bit more effort. And I'm just going to draw another picture again here. So our ball comes down. Now we know the x component from our previous work. We just solved for it. That x component is 3.02. So let me just blow this up here. Here is the velocity arrow as it goes into the ground. The velocity arrow as it goes into the ground looks like that. And here is the x component, which we know is 3.02. What we need to figure out is what is this y component. We need to figure out the y component to know what the total velocity is. Now, just to say this, initially, the total velocity for y was 0. But now it's not anymore, and so we need to determine what this is. And we have our information. We have our acceleration due to gravity. We have the displacement. It fell, just looking back at my other piece of paper here. We also know the time, because we already solved for that, 0.364. And what we're looking for is final velocity. And we can get this one from the first equation that I've usually written on the board here. We can get final velocity here. So we have initial is 0, minus 9.8, which is a, times the t that we solved for. And that is our final velocity, 0.364. Times 9.8 is, and of course it's going down, so it's negative. I just didn't put the minus sign in Google there. 567. So there is our velocity going down. So we just figured out this y component. So let me draw this a little bit bigger here to be clear. Here's our final velocity vector as it impacts the ground. We have the x component, 3.02. I just figured out the y component. It's going down at minus 3.567. Now that we have these two components, we can use Pythagorean theorem to figure out what the actual length of the velocity arrow is. And that is the velocity then. The velocity in 2 dimensions is always going to be these two components. So if we look at this final velocity, that means it's going to be this going to be Pythagorean theorem. So let me figure out what that is. And no, I'm not. I didn't put the minus sign in there because, you know, it doesn't matter when we're squaring something that'll take out the minus sign. So I just didn't write it in, you know, save myself a little bit of typing. So I get a final velocity of 4.67. That is the magnitude of the velocity just at impact. And they went with 4.68, so, you know, just some minor rounding error somewhere. You can see here my rounding is to 4.67, but, you know, I used a time value, or I used both of these values, which are both rounded numbers. So using 2 rounded numbers, not surprising that my answer is going to have some rounding error in it as well. But again, close enough that it takes it, and it should. Good stuff. So what's this last part? Find the direction of the velocity. So direction, easiest to get from tangent. Why? Because once we have the opposite and adjacent legs, then tangent we can use to get the angle. So tangent, the y component over the x component. So our y component was minus 3.567. The x component, 3.02. So I'm going to do inverse tangent on that. Oh boy, I've never tried doing inverse tangent with Google. I'll probably have to use arc for terminology. So I'll just use arc. Arc, in case you don't know, let me get this out of this way. In case you don't know, this notation, tangent to the minus 1, is the same thing as writing arc tangent. Means the same thing. Means the same thing. So I have arc tangent of negative and that is in radians. That's right. Because Google always calculates in radians. So I'm going to take that radian answer and convert it to degrees. And I wonder if I can just do 180 divided by pi. So we get about 49.7. And now my calculator's not even new batteries haven't made it work. So, you know, I hope you have a calculator. You just got to push the inverse tangent button. Make sure your calculator is in degrees so you don't have to do any converting. So 49.7. And, well, let's see if they take it. Because it does say below the horizontal. Below the horizontal is what means a minus sign. So, again, I had 49.7. They say 49.8. That's just a rounding error. But let me just say this really fast. That yes, my scratch paper is of like old stuff that never got used, so I don't waste that paper. But let me just say this really fast with a coordinate system. This is considered a positive angle, positive rotation. This is considered a negative angle, a negative rotation. And this angle here below the horizon means this type of rotation actually means a negative angle. So for instance, negative 30 degrees is 30 degrees below the horizon. I'd be interested if they'd accept the minus sign, but well, there it is. There it is. Just in case you're curious if there should be a minus sign there or not. I don't know. Probably not, because they say below the horizon, which is the negative sign. So, like if you say two, like if you say left 2, like that. Well, if you say left -2, that's kind of redundant. So that's just what I'm saying there. Maybe I'm being too ticky-tacky. We'll go to the next one. I just had to use tangent. I just had to use tangent to get that answer, and it was the right answer. Just to give you that confidence. Just use the tangent, and that got us the answer. So what about this? We have a daring swimmer diving off a cliff, and they're going to take a running leap. Now, are they... Okay, so here's another thing with reality that's a little weird, because, you know, if you're going to jump off a cliff, you're probably going to jump like that. But notice our picture. Notice our picture. Our picture says the person is going to jump like this. So they're going to jump perfectly horizontally. We're not going to pretend if you can do that or not. We're just going to assume you can, because we want to keep the math relatively straightforward. So this person is going to jump perfectly to the right so that their y initial velocity is 0. They're not jumping up or down. They're just going to jump to the right with some velocity. And that does help us helps the math a little bit easier here. So what must her speed be as she leaves the top of the cliff so she will just miss the ledge at the bottom? So we got some info. So we know her initial velocity in the y direction is 0 because she's going to magically just jump to the right. We know the acceleration is due to gravity, minus 9.8. And we also know she's going to go through a displacement. And what is the height? The height here is 9.3. Now remember, the person is falling down 9.3, so that is in the negative direction. And I just want to say this again. If this isn't negative, then what you're saying is this person jumped off the cliff and then floated up. That's what the positive would mean here. But that's not what happens. The person jumped off the cliff and they went down. That's what the negative indicates. Very important to have that minus sign there. And they also tell us that she needs to travel a distance of 2.35 meters. So now remember, in the x direction, we only have this one equation in the x direction. And they're telling us x is 2.35. And then right here is the velocity we want to solve for. What is the minimum velocity to satisfy this information? And here is that velocity we want to solve for, which means we need time. We need time. This information, 3 pieces of information, this will get us time. And from this equation that's used a lot is how we'll get it. So we know the displacement is minus 9.3. We know the acceleration due to gravity. And we know the initial velocity is 0. So here's the equation we need to solve. And so we have minus 9.3 divided by minus 4.9 is our t squared. And so let me figure out what that number is quick. Uh, 1.38. And now that we have a time, well, let me get that out of the way. Now that we have a time, we can plug it in here. So now we know 2.35 equals v times 1.38. And so we can solve then for the minimum velocity she would need to just clear the edge. So that'd be 2.35 divided by 1.338. Now, why do we say minimum? Because, if the person jumped really fast, then they would, they'd obviously clear the ledge. So the faster your speed, you will clear the ledge. So we're looking for the minimum speed. The minimum speed where she's just going to clear the ledge. And that's what it is, 2.35 divided by 1.38. So she would need a minimum velocity of about 2 meters per second. That's actually not very fast at all. But remember the ledge here? The ledge is only 2 meters here. So that's about, a little bit more than the length of a person. While you're falling almost 10 meters, that's about, more than the length of 5 people. So 1.7 is the answer here. And again, no penalty for significant figures. 1 or 2 decimal places in your answer, that's good enough for me. Because getting this number, I think, is clearly the hard part. Getting 1.71, much, much harder than, how many significant figures you have. Let's check out the next one. So we've got a batted baseball. Lee's at that. Oh, no, it's in feet. Really? All right, we're going to have to convert that feet right away. So we have baseball leaves a bat at an angle of 30 degrees above the ground. So I'm going to draw my picture here. Here's 30 degrees above the ground is this baseball. There it is. And it's caught by an outfielder 395 feet away. All right. Well, you know what I'm going to do? I'm going to go from feet to meters conversion. There it is. And so I have how many feet? 395. And that is 120.4 meters. So there you go. There's my conversion. I'm done. So this is our distance in the x direction. So the ball was hit. And another thing we're kind of assuming, which isn't necessarily... Oh, no, it does. It does. I was about to say something, but it actually says it right here. Both players are the same height. So we're ignoring the height of these people because we're just going to say that they're exactly the same height. So the ball was knocked and it was caught at the same height. So in essence, we're ignoring the height of the human being here, which is fine. Just makes the math a little bit more complicated. So we need to figure out the initial speed of the ball. And notice the speed isn't given anywhere here. So we'd have to write this out, where the x component is going to be whatever our velocity is times the cosine of the angle, while the y component will be whatever that velocity is times the sine of our 30-degree angle. And in the x direction, we've got gravity. I'm sorry, in the y direction, we have gravity. In the x direction, we have the displacement where it was caught. And again, I already converted that to meters. So remember, there's only one equation in the x direction, and that's it. We know x is 120.4. Our velocity is the x component of velocity is a v cosine 30, where we don't know v yet, and we don't know time yet. Going over to the y direction, remember it goes up and comes down, which means its total y displacement is 0. It started and stopped at the same height, so its y displacement is 0. So we can take this information and plug it into what tends to be the favorite one used, which is this one. It's always a favorite that's used. And we'll just plug our stuff in. We know y is 0. We have 1/2 of minus 4.9. We have our t squared plus our initial velocity, which is this v sine 30 times t. We'll divide everything by t, so we'll solve for t. So we have minus 4.9. Again, that's a half of 9.8. I put 4.9. My brain did that calculation. Remember, that's 9.8. A half of 9.8 is 4.9. So my brain jumped the gun there a little bit. And then we got our t, because we're dividing out a t. And with a v sine 30. So we're solving for t. We're solving for t. And there it is. Minus signs will cancel each other out. This is t. Now we still don't know v, but that's all right, because we can now plug that in up here. So that's what we're going to do. So we have 120 v cosine 30. Our time is v sine 30 over 4.9. And notice we can combine the v's to solve. So v times v is v squared. I'm going to multiply both sides by 4.9. And there is v squared. I know it's getting a little bit ugly there, but why don't I write it on another piece of paper right here? So my final answer is equals v squared. And then, of course, in our calculator, we'd have to take the square root of all that, and that would be our answer. And I'm going to pause for a moment because it's going to take me a moment to type this all into Google. All right, so just typing it in. You know, we have sine 30, which I'm just going to use my brain. I know that's a half. And in cosine 30, again, just using my brain, I know that's square root of 3 over 2 instead of using my calculator. And that's what I typed in over here. So I do have 0.5, a square root 3 divided by 2. And let's see what that gives us. That's actually v squared, 1362. I need to take the square root of all that, so I need to do that actually again. So I'm going to put square root, parentheses around all of that. And there we go. That's what v is. 30. I'm just going to call that 37. 36.9. I'm just going to call it 37. And that's my answer. 30. I'm just going to go with 37. It didn't like that, huh? All right. Well, I'm just going to request it. Maybe I rounded too much. Oh, it's... They wanted it in feet. Of course. Of course. Why? I mean, it does say it. Fair enough. It says feet per second. I totally ignored that because I'm a physics person. Everything should be in meters per second. So I did totally ignore that. So there we go. I just went to another meter to feet conversion. So my answer was 37. You can see if I convert 37 meters, that is 121 feet, which is the answer they have there, 121 feet. So fair enough, fair enough. I did not put my answers in feet. It does clearly state that, but I won't do that to you on a test. We'll always be in standard units there. What's this next part? How high does the ball rise above the point where it struck the bat? So wants to know its maximum height. Maximum height, of course, given by final velocity is 0 in the y direction. And we know acceleration due to gravity. And now that we know the velocity, I'm still going to work in meters. Now that we know the velocity, we can get the y component of velocity, because remember that's going to be sine of our angle there. And what was the angle here again? 30 degrees. And maximum height, we can then use this equation that's used sometimes, not too much, but we can use this one again. This one usually pretty easy when you have a final velocity that's 0. Then we would have 37 sine 30 squared plus 2. Our acceleration is minus 9.8. And then we can solve that for y. And let me do that. So I'll move this to the right side. And then this is negative. I'm also going to, so 2 times, I don't know if you can hear me so far from the mic. 2 times 9.8, so that's going to be our 19.6, and dividing by that, and it's negative. And there is our y. And again, the negatives should cancel to give us a positive height. And I'm going to, I guess, cheat. Well, not really cheating. I'm using math. Because I have to type it into Google. So I'm just going to use some properties of exponents. This 2 can pass along to the 37 to make that squared. Sine of 30 is a half, and I'm squaring that again from that square. And then this is divided by 19.6. This is what I'm going to type into Google then. 37 squared, 0.5 squared, 19.6. 1/2 squared is a fourth, which is 0.25. And then dividing by 19.6 to get me 17. What am I solving for? Y is 17.5. I'm just going to go with the 17.5 on that. Now that is in meters. That is in meters. So I'm going to go over here. 17.5 is 57.4 feet. 57.4 feet. And there we go. Put it in feet that time. So just, I want to be very clear about this problem. This is actually a really good problem. It is. This is a good problem. I also consider this to be a good test question, but I would never do this feet thing to you. So I just want to make that clear. This is a good type of test question, but I will always give it to you in meters and in proper units, so you don't have to worry if you're going to get caught off guard by, say, it wants your answers in feet. So something else I just want to quickly say that I notice in looking in Pearson here, they're giving this, which is commonly called the range equation. There it is. And notice I solved this. I solved this entire problem without ever referencing the range equation. So if the range equation is something you like, I'm not saying you can't use it. I'm not saying it's bad, but I'm saying you don't need it. I solved this entire problem by just using the kinematic equations that we've been discussing all this time. So if you feel the range equation is something else you need to write down, that's up to you. That's up to you. But I just want to make it perfectly clear. I didn't use it at all, and I got both answers right. So it's not needed. All right, so let's check out the last one. Some bug that hops frogs, I guess. The context is actually pretty irrelevant, if not totally irrelevant. What matters are the numbers. We have an angle of 58 degrees. And they reach a maximum height of 58.7 centimeters. Now centimeters, nice and easy to convert to to meters, because we just got to move the decimal place twice. This is 100 centimeters in a meter. We also know the acceleration due to gravity. And we know at the top of the height, final velocity is going to be 0. So from this information, we can actually figure out what the initial height is. The initial velocity, by using this result. We can find the initial y velocity So final velocity is 0 at max height. Our initial is what we're solving for, plus 2 times the acceleration due to gravity, and our max height, and then 2. I'll just move all this to the right side to solve for v. So again, 2 times 9.8 at 19.6. And then take the square root. There is our initial velocity. So square root to get 3.39. Now this is in the y direction. So what we just solved for was this component right here. This initial here is 3.39. Now remember, the total speed is the vector. The total speed is the vector. You can see right here they're asking for v. They're not asking for v sub y. They're not asking for the velocity in the y direction. They're asking for v, which is the actual velocity of the left or the right and up motion, which means Pythagorean theorem or trig functions. So this picture, putting into trig, we have our hypotenuse, we have the opposite leg, and we have this angle. So we can use sine, which equals the opposite leg over the hypotenuse. And then we can solve for b by just doing a little cross multiplying there. Now to do sine of 58, since Google always works in radians, I do need to convert that. So what am I typing in? 3.39 divided by, so there I put sine of 58, but I do need to convert this to radians because that's how Google always works. So in case you don't remember, I need to convert degrees. We do this with, oops, I guess you can't see that because I got this in the way. So we have 58 degrees. To convert this to radians, pi is 180 degrees. So the degrees will cancel, will be left in radians. So this is the conversion factor I need to put into Google here, pi over 180. So times pi divided by 180. That closes our sine, and we should be good. And so we get the velocity is 4. I'm just going to round that to 4, 3.997. I'm just going to call that a nice good 4. So this vertical component, 3.39. The total velocity is about 4, which means the bug isn't moving too far to the right. So this picture that I've drawn may be deceptive. Let me try a different picture to try to be clear with the numbers we have. That we have a picture more like this, where the bug jumps pretty high, 3.39, but only jumps a little bit, just a little, to the right. Now, we could figure out what that number is, but it's not asking us to. But just trying to draw you the picture. So that one a little bit deceptive because I didn't know the numbers yet. But now that we know the numbers, the picture looks more like this. Pretty, you know, the bug, instead of the bug jumping like this, the bug is jumping more like this. And so their x component of velocity is pretty small. So I'm just going to say it's about 4. Let's see what Pearson thinks about 4. And they'll take 4. I actually took 4.00 right in the nose there. And let's check out the last one. What horizontal distance is covered? All right. So now to figure out the horizontal distance, we will need the time in the air. So Going back to that other page is pretty messy. So going back to our information, the time in the air means a displacement of 0 because the bug starts and stops at the same height. So its height displacement is 0. The acceleration due to gravity. And we also figured out the initial y component, which was 3.39. And that's enough information to figure out time from this equation. So we know the total displacement is 0, acceleration due to gravity. We're trying to figure out time. We have an initial velocity up. We can solve this by just dividing out a t. And then solve for t. And see what that is. 3.39, 4.9. Is 0.69. So that's our total time in the air. The total time in the air. Remember, in the x direction, the only equation we have is x equals vt. They want us to know what x is. Okay? Now we do need to figure out, remember I said this is a little displacement, little velocity. We do need to figure that out. That x component is going to be the hypotenuse, which was 4, and cosine of, what was this angle, 58 degrees. Let me just explain that clearly unless you're not understanding that. So we know of this right triangle, we know the hypotenuse, we know the opposite leg. We could use Pythagorean theorem to get the last leg, or we could just use a trig function to get that last leg, because we know the angle here as well. So there's multiple ways you could get this, but just to be clear, sine is opposite, or I'm sorry, cosine, I'm using cosine here. Cosine of our angle is adjacent, which is this little part we need to figure out, which is technically the x component, divided by the hypotenuse, which we figured out is 4. And so multiplying both sides by 4, I get the Vx component is 4 cosine 58. So that's what I have for my x component. It's 4 cosine 58. And then the time value we just solved for, 0.69. There it is. That's my result. I need to again punch this into Google, and I need to convert that 58 to radians since Google works in radians. I don't know, I feel like I might have typed an error in there, but I'm just going to assume I didn't, even though a little voice in my head is saying I should check. I may have typed in something wrong, but I'm not, I don't know. You know, sometimes you get the feeling like you may have made a mistake, but I'm going to ignore the feeling and just put in what the answer I was given. And maybe my feeling was correct. All right, so I looked and looked. I couldn't find any mistake in my work. I couldn't find any mistake with anything I typed in. And look, it's because they wanted the answer in centimeters. So my answer was 1.46, but that's in meters. And that is 146 centimeters. So again, I won't do this to you on a test. And I understand it's in centimeters here. I can also understand maybe another professor wanted to come down on me and saying, well, look, it says right here, express your answer in centimeters. I see that, I do. But this one also said use standard units. So to switch units like this in the middle of a problem, especially for students learning the material. I just think it's highly problematic. Why even do this? Either way, I admit I missed the attention to detail there as well, that it should be in centimeters. But I just want to stress to you again what I think the truth is. What I think is important here, that you can get this number here. That to me is what's important, because that means then you're doing all this right. And then the fact that there's a conversion at the end that we need to do is just, to me, just kind of a bothersome, annoying thing that I think is more, it's more problems than it's worth. So sure, I got caught. I didn't put it in centimeters. Maybe I'm defending myself. But I'm just saying, I don't do this to you on a test. I would never change units in the middle of a problem like this. And again, if this occurs to you in a quiz or something, absolutely send it to me. So another point I'm trying to give here is that I'm trying to be understanding of what are issues that I think students have. And this is one of them. When you change units in the middle of a problem, I just don't think that's good for students learning physics. So there it is. There's the homework. I'll see you Tuesday. Actually, there's something really quick here I want to say again. And just another reason why I have problems with doing units like this is because notice I entered in 1.46 and it just told me I'm incorrect. And this is what I think about as students, that you go through all this work. Maybe you're even confident you did it right and you got your answer 1.46, and then the computer says, oh, that's just wrong, try again. There's no suggestion here that you have the right answer, but it's the wrong units. There's no suggestion here at all. It just says incorrect, try again. And in my experience, what that causes the students to do is to think this was wrong, that they made an error here somewhere. And that's the same thing I did. When I saw the computer tell me I was incorrect, I went and I double-checked all of my work again. I checked my calculations, and I couldn't find a mistake. And that's just, again, why I'm trying to stress that I won't do this to you on a test. I do think this is a trouble. If the computer would at least tell us that, hey, that was good work, you just didn't do the units correct, then I'd be okay. It's the fact that the computer says incorrect, try again. That's what bothers me, because the answer is technically 100% correct. It's just not in the units they wanted. So I just had to say that again and show you the actual screenshot of the computer saying incorrect, even though 1.46 is absolutely the correct answer. It's just in meters. So there you go. Now I'll see you Tuesday.